are going to discuss the interaction picture in Wick's theorem. And this is going to give us enough so that we can calculate scattering amplitudes. So it's been over the last few lectures, what we've been trying to do has been to compute scattering amplitude. And last time we saw we could relate the scattering amplitude to a time-ordered product of fields. And today, what we're going to do is we're going to relate this time-ordered product of interacting fields to a time-ordered product of free fields. By going to the interaction picture. And then we will compute this time-ordered product of free fields by relating this time-ordered product of free fields to the Feynman propagator that we computed in the first lecture. So this is our strategy for computing scattering amplitudes. And so this was the LSE reduction formula that allowed us to relate scattering amplitudes to time-ordered products of interacting fields. And today, we'll discuss these two links. Here, we can do this by going to the interaction picture and this through Wick's theorem. And this is the Feynman propagator that we computed a few lectures ago. So that's where we're going. And a little bit farther in the future, we will see a more direct link between the Feynman propagator and the scattering amplitudes using a technique of Feynman diagrams. So that's where we'll go next week. Today we'll compute everything we need. We'll learn enough to, in principle, be able to compute the scattering amplitudes, but we'll learn a faster way next week. It's entirely equivalent to what we're doing today and what we did yesterday. OK. So that's where we're going. So in order to do this middle link, this picture, we need to go to the interaction picture. So what is the interaction picture? It's kind of a hybrid between the Schrodinger and Heisenberg pictures. And so our basic technique is going to be perturbative in nature. We're, in general, not going to be able to, for an interacting theory, compute any scattering amplitude exactly. But we can do it at any order in perturbation theory we like. So we're imagining that our Hamiltonian is given by a free part, which for us is just either the real or complex Klein-Gordon Hamiltonian. And we'll imagine adding some interaction Hamiltonian, which an example we'll look at in more detail next time it's called phi-4 theory, where we had an interaction theory that just has a lambda over 4 factorial phi to the 4th. Okay. So as you know, in the Schrodinger picture, the states evolve. And since we're going to be switching back and forth between the pictures fairly frequently in lecture, I'll label our states and operators for the most part with subscripts that indicate whether we're in the Schrodinger picture, the Heisenberg picture, or the interaction picture. And in the Heisenberg picture, the operators evolve. And the operators in the Heisenberg picture are related to the operators in the Schrodinger picture, the usual way. And I just want to introduce some different notation for this. So these e to the iht we can define to be time evolution operators, which I'll denote by u or u dagger of t and 0. And so you can think of this as just this is just a time evolution operator that evolves either a operator in time in this way, or if we acted with this on a state, and the Schrodinger picture would evolve the state in time. And so in general, u of t prime is equal to minus I h t minus t prime. And u dagger just flips the sign here. Okay. So that's nothing new. So the interaction picture is a hybrid between the two. So in the interaction picture, the operators evolve with the free Hamiltonian. So the operators in the interaction picture are related to the Schrodinger picture operators with the free Hamiltonian. And the states evolve with the interaction Hamiltonian. And we'll see that in a minute. The way the states are defined in the interaction picture is that states are defined to be e to the I h naught t times the Schrodinger picture states. And this implies that they satisfy a Schrodinger equation where instead of the Schrodinger picture Hamiltonian, we have the full Hamiltonian. We just have the interaction part of the Hamiltonian. And we can see that as just by plugging in this definition into the Schrodinger equation.
And should that be chi in the exponent?
No, it should not. So yeah, so to see what this means, let's write down the Schrodinger equation. And so if we then multiply this equation by e to the minus I h naught t, we can write this in terms of the interaction picture states. And then what we get is e to the minus I h naught t psi I is equal to, let's write out the Hamiltonian as the free and interaction part. And so if we do this derivative, we get two terms. So we get one term when the derivative acts on the exponential. And that term will just cancel off the first term over here. We would just get h naught e to the minus I ht times psi. So we're only left with one term. And what we have over here is I dt. Psi I is, so after we multiply by e to the I h naught t, over here we were left with I h int in the Schrodinger picture e to the minus I h naught t times psi in the interaction picture. And this product of operators in front of the state is just the definition of the interaction picture, interaction Hamiltonian. So this is equal to the interaction picture, interaction Hamiltonian, which I'll denote as HII. So that's what I mean when I say that the states evolve with the interaction Hamiltonian. Even though they're defined like this with the free Hamiltonian, they satisfy a Schrodinger equation with the interaction Hamiltonian. Okay. So let's try to solve this equation. And let's make the ansatz that our solution takes the following form. That the solution at some time t is just some unitary time evolution operator. Acting on the state at some earlier time, t naught. And so if it's a time evolution operator, it should satisfy a composition property. So we should have ui of t1, t2, ui of t2, t3 is ui of t1, t3. So if we time evolve from T3 to T2 and then T2 to T1, that's the same as evolving from T3 to T1. And it should satisfy an initial condition that if we evolve for no time, we should get back the identity operator. Okay. So if we plug this ansatz into the Schrodinger equation, what we get is a differential equation for the time evolution operator, which is this differential equation. And you might guess that the solution to this equation is just the exponential minus I integral hi I of t prime dt. So that this is a simple differential equation, and if these were functions instead of operators, this would be the solution. However, they're operators, so this is almost right. It's not going to be quite right. And let's see what the problem with this guess is. So this guess almost works. So let's compute the time derivative and see what the problem is. And this is our guess. And so exponential can define it through its series expansion. So this is just d dt of 1 minus I integral t naught t hi I of t prime dt prime. And in the next order, minus I squared 2 times this integral squared. Okay. And we can compute the derivative. And so the first term is straightforward. Let's get hi I of t. The next term, we get minus I squared over 2. Then we get two terms. So we get hi I of t times the integral. And we also get another term where the integral is first. So this is not quite the same as hi times our first order term. We can't commute these hi of t prime with hi of t because these are operators. And in general, hi of t does not commute with hi of t prime. So this is the problem term. Okay. That's it wasn't a bad guess though. We'll find a solution that looks almost identical to what we first guessed. And we can do that just by direct integration of this differential equation. So if we just directly integrate the equation, we get u of t and t naught is a constant, which has to be 1 due to our initial condition that ui of t and t is 1. Then minus I integral t naught to t hi I of t1 ui t1 t naught and t1. Okay, so if we directly integrate it, we still have the I on the right-hand side. But we can just then iterate. So we can plug in this equation in for UII, and we'll get we'll have a series solution for UII. So if we iterate this, we get that UII, or UI of T and T naught is just a sum of minus I to the n of the series of integrals. So first integral is from T naught to T. If we plug this in once, our upper limit of integration becomes T1 instead of T. And so on up to T naught to Tn minus 1, Tn. And we've got product of HIIs. And these HIIs are time ordered because of our limits of integration. We have that T1 is greater than T2, and similarly greater than or equal to, and similarly T2 is greater than or equal to T3, and so on. So we've got here a time-ordered product of operators. Okay, so I claimed that this wasn't a bad guess and our solution would look something like that. So let's try to put it in a form that looks more like that. So if we look at the difference between...
There's still a layer at the top.
Sure. So if we look at this last line, it's not quite what the series solution, or a series expansion of an exponential. But if we play with it a little bit, we can put it in a form that looks more like an exponential. And to do that, let's just look at one term in this series. And the first interesting term is the second order term, which is just integral T naught to T, T1, integral T naught to T1, T2, HI of T1, HI of T2. And so here, this integral, we are in the T1, T2 plane, integrating from T naught to T and T naught to T, subject to the restriction that T1 is greater than T or equal to T2. So we're integrating over this triangle. So left-hand side of the equation integrates over this triangle. But if we extended the range of integration to integrate over the whole triangle, everything would be the same in the upper left triangle as long as we time order the operators. So then we just get the same contribution from the upper left triangle as the bottom right triangle. And so we can write this as a half, because we're double counting, times the integral from T naught to T, dt1, integral from T naught to T, T2, times the time-ordered product of HII T1, HII of T2. So the right-hand side integrates over the entire square, but double counts. And so now we have a half, which is the same factor we'd have in the expansion of the exponential. And if we did a similar sort of manipulation for the higher order terms, we could write the solution as follows. So we can write it like this. So we still have the minus I to the n. If we did this with n integrals, we would have an n factorial instead of in the denominator instead of a 2. And we'd have just the integrals. All of the integrals would go up to t. And we'd have the time ordered product, hii t1 up through hii tn. And so this looks exactly like our naive guess, except we have this time ordering. So we can write the solution as the time-ordered exponential. And this is what's known as Dyson's formula. And so we'll see in a few minutes, we'll see that we can use this formula in order to do the middle step in our diagram on the first board in order to relate the time-ordered product of interacting fields, time-ordered product of free fields. And so this is the most useful form of the solution for the time-ordered, for the time evolution operator, the interaction picture. And we'll use this when we relate the time-ordered products in the free and interacting theories. So we'll plug this into our formula in a minute. But what we need to do in order to do this step here now is figure out how the fields, the vacuum state, and also the interaction Hamiltonian, what they look like in the interaction picture. We'll need explicit formulas for those, and that's what we'll do next. And after we do that, we'll be able to do this step. So where is this? The first thing we can write down are the fields in the interaction picture. And So we know that the fields in the Schrodinger picture write down as follows. So we're doing something a little bit different from before. We're just demanding that in the Schrodinger picture, the fields look like this at some time t naught instead of at t naught equals 0. And this is just for later convenience. So if we do that, then we can write the fields in the Heisenberg picture as e to the I h t minus t naught. And I'll just denote t minus t naught as delta t. And so then we can just use the definition of the operators in the interaction picture to write this as e to the I h delta t, e to the minus I h naught delta t. Sorry, we can insert the identity here in the form of e to the minus I h naught delta t, e to the plus I h naught delta t. And similarly over here, and identify this using the definition of the interaction picture operators as phi I. And this, I claim, is the same thing as the time evolution operator we just computed, or the conjugate of it. And this is the time evolution operator we just computed. So this is will be another useful form for the time evolution operator in the interaction picture. And it's not at all obvious that this is the same operator as the expression we have over there, but we can see just a few lines that it satisfies the same Schrodinger equation. So if we compute I dt of e to the I h naught delta t, e to the minus I h delta t, what we get is e to the I h naught t minus h naught from the derivative of the first term, and plus h from the derivative of the second term, minus I h delta t, which is the I h naught delta t. Times the Schrodinger picture interaction Hamiltonian. And in this last line, we can again insert the identity here to get e to the I h naught delta t, h I s, e to the I h naught delta t, e to the plus I h naught delta t, so minus I h delta t. And this first term, first product of the first three operators, is just the definition of our interaction picture, interaction Hamiltonian. And the product of the second two operators is what we're claiming as ui. So it satisfies the same differential equation, has the same initial condition. We set delta t equal to 0. We get 1. So these are the same operators. And both expressions will be useful. Okay, so what's left? So what's left is to figure out what the interaction picture, interaction Hamiltonian looks like, and what the vacuum looks like. The first task is very straightforward. Due to our result for how the fields, what the fields look like in the interaction picture. So if we have an interaction Hamiltonian that, say, is integral d3x lambda over 4 factorial phi to the 4th, then our interaction picture, interaction Hamiltonian, will just have exactly the same functional form. Or we just replace all of the, say, Schrodinger picture fields with interaction picture fields. That's because all the factors of u will cancel out in between the factors here, and we'll just be left with one on each side. Or if it's going from the Heisenberg picture to the interaction picture, we'll just we'll have a u and u dagger that will cancel. This is the easiest step in going to the interaction picture. Just replace the field in either the Heisenberg or Schrodinger picture with the interaction picture fields. So the last thing we need is, in order to compute the time-ordered products that we're interested in, is to figure out what the interacting vacuum looks like. Okay, so we want to relate the interacting vacuum of the interacting theory that we're interested in to the free vacuum of H naught, our unperturbed Hamiltonian. And the way we're going to do this is we're going to consider the time evolution using the full Hamiltonian of the free vacuum. And we can insert a complete set of states here. So where we'll write 1 as omega omega plus sum / integral over all of the other states. So again, there are some discrete and continuous parameters that characterize the other states. And okay, so if we do this, what we get is the following expression. That involves the interacting vacuum that we're interested in, and also has a whole bunch of terms that we don't particularly care too much about. Okay, so what we want to do is keep this term and get rid of these terms. And we can do that. So small t and capital T right now, there's no reason at this point why I didn't just write this as one time, but it will be useful to send. We're going to send big T to infinity in a minute, and small t it'll be useful because of the time ordering we have over here. It'll be useful to leave a finite leftover part after we send the amount of after we send. We're going to send big T to infinity and keep small t t not finite. Okay. So this is an equation we can solve for the interacting vacuum. So we can solve this equation for the interacting vacuum. We can write omega is e to the minus I h t plus t naught, 0 over e to the minus I h t plus t naught, negative 0 omega, minus 1 over omega 0, some integral of e to the minus I so before I finish doing that, it'll be useful to introduce the notation. So let's assume that E naught is the energy of the interacting vacuum, and that the energy of the free vacuum is 0. So using that, I can replace. So this came from. Oh, I've already done that here. I didn't explain it. So that's how the H we can't replace with E naught. And over here, we can write this as I En minus E naught, T plus T naught, N 0. Okay. So this is a term we like. It's simple. It only involves the vacuum of our unperturbed theory. And so we'd like to keep this term. This term, on the other hand, is much more complicated. It involves a sum over all of the other states in the theory. So this formula is not particularly useful unless we can get rid of this formula, these extra terms. And we can do that if we assume that the ground state is unique, so that En is greater than E naught for all n. And if we take the limit at t goes to infinity in the complex plane in a direction that has a small negative imaginary part, because then these terms will decay much more rapidly than these terms. So in that limit, we can neglect these terms. So this gives us a useful formula that relates the vacuum of our unperturbed theory to the vacuum of the interacting theory that we're interested in. Now we can, if we do a little more work, we can put this in an even more useful form. So because we're assuming that the energy of our free theory is 0, if we act with the evolution operator, the free evolution operator, time evolution operator on the free vacuum, we just get back the free vacuum. And so that implies that we can write the numerator, which only involves h, in terms of our expression here for the time evolution operator in the interaction picture. So we're free to insert e to the I h naught t plus t naught here. It doesn't change the expression. And so we can write omega as the limit t goes to infinity in slightly imaginary direction times ui of t naught minus t 0 over e to the minus I e naught t plus t naught. I guess 0. And similarly, we can write omega, the bra, as limit t goes to infinity minus I epsilon 0 ui t t naught to the minus I e naught t minus t naught 0 omega. So in this second expression, I've changed the sign of t naught relative to what you'd expect if you just took the dagger that. But we never assumed anything about the sign of t naught to begin with.
In the interaction vacuum, we're evolving the free theory vacuum with the Hamiltonian method. I was wondering why there's no minus sign in the exponent.
Oh.
Well, it's like minus t minus
Yeah, so you could, right. Yeah, so if there was a minus, we could just think about this, we're sending it backwards in time. Or
But and then the expression in the bottom way after exponential minus I.
yes. So that's inconsistent, I guess. So there I've got the minus. So here, let's just put the minus in everywhere. Thank you. Thank you for catching that. Okay. So we're almost done. All that's left to do is put together our results. So we've computed basically all of the elements we need in order to compute the time-ordered, to relate the time-ordered product of interacting fields to the time-ordered product of the free fields. And let's put it together. So for simplicity, let's just look at time-ordered product of two free fields, or two interacting fields. It will work similarly if we had more. And again, for simplicity, let's assume x naught is greater than y naught, and y naught is greater than t naught. So in this case, these fields are already time-ordered. And we can just plug in our results. So we've already computed what the vacuum is and what the fields are. So we can just use our results. We've got the limit as t goes to infinity, 1 minus I epsilon. We've got, I'll just combine I'll write the denominators of the vacuum states first. Got minus I E naught t plus t naught, omega 0, 0. And from the other term, minus e to the minus I E naught t minus t naught, 0 omega. Then this is all multiplied by 0. Everything is already time-ordered, so I don't need to worry about that. Then we have ui of t naught. Then writing the field in the interaction picture, the field is equal to ui dagger x naught t naught phi I of x ui of x naught t naught. Then we have similarly for uy. And finally, we have another time evolution operator from the numerator of our expression for omega. And it's time evolution t naught to minus t 0. Okay, that's a rather long expression. Unfortunately, it simplifies dramatically. And to see that, can note that we can choose the normalization of our free vacuum to be unit normalized. And if we do that, then just combining our results at the bottom of this top board, we get 1 over 1 is equal to 1 over omega 0, absolute value squared, times 2 e to the minus 2I e naught t times 0 ui of t naught ui of t naught minus t 0. Okay. And the next thing we can do is we can use the composition property of our time evolution operators. So time evolution from minus t to t naught, followed by time evolution from t naught to t, is the same as time evolution from minus t to plus t. And we've got a bunch of products of time evolution operators where the last and first arguments are the same. Also, we should remember that u dagger, say, of y naught t is the same as u of t naught y. So this is the same as u of t naught y. Why not? So with those two facts, these two we can write as a single time evolution operator. Same here and same here. And so this simplifies our expression. So what we're left with then is omega t phi x phi y.
Dan, are we still in the limit of
Here?
Yeah.
Yes, there should be a limit. Thank you. So putting this together, we get that this expectation value is the limit of 0 ui t x naught phi I x u x naught y naught phi I y u of y naught minus t omega over 0 ui t minus t 0. And so everything here is time ordered. So this is time ordered. So I can put in a time ordering symbol here. And that means I can further combine the ui, this should be a ui also, further combine ui of t and x naught with ui of x naught and y naught with ui of y naught and minus t. So I can write this then in our final form, which is the limit t goes to infinity, 1 minus I epsilon of 0 times the time-ordered product, the interaction picture fields, times ui of minus t to t, which, using Dyson's formula, is just a time-ordered exponential, minus I, integral from minus t to t dt, hi of t 0 over the same thing in the denominator, just without the fields. And so this is our final result. And so, as promised, we've related the interacting fields to, in the Heisenberg picture, to interaction picture fields, which behave just like free fields. And related the interacting vacuum to the free vacuum. So made a considerable amount of progress. The right-hand side, so far we've made no approximations. Right-hand, these two quantities are exactly equal. To proceed further, though, we're going to need to make some approximations. Computing these time-ordered products involving exponentials is hard, but we can do it perturbatively. So if we write the exponential of an operator as 1 plus a plus and so on, then we can compute the numerator and the denominator perturbatively. And so that's what we're going to learn how to do next. So each of the terms, after we've expanded out the exponential, will contain a time-ordered expectation value of some product of fields. Again, assuming the interaction Hamiltonian is just something like the integral of phi 4. So that's a typical interaction Hamiltonian we're interested in. And so then each term in the series expansion of the exponential will just be a expectation value of a time-ordered product of fields. So that's what we need to learn how to compute next. And in the last part of the lecture, that's what we'll do. Any questions on that? Okay. And also, from now on, we're, unless otherwise stated, always going to be working in the interaction picture. So I'll drop all the i's from now on, just to save some writing. All right. So the final ingredient that will allow us to compute scattering amplitudes is known as Wick's theorem. And what Wick's theorem does is it relates time-ordered products of fields to normal-ordered products of fields. Normal-ordered products of fields are particularly convenient when we're taking a expectation value, because the expectation value of any normal ordered product of fields, where all of the creation operators are to the left and all the annihilation operators to the right, is 0. As long as it contains at least one creation operator or annihilation operator. So that's what we're going to do, is we're going to relate time-ordered products of fields to normal ordered products. And to do that, it's useful to separate out the parts of our field operators that contain creation operators and the part that contains annihilation operators. So we will decompose phi into two parts, a positive frequency part, phi plus, which contains the annihilation operators. And a negative frequency part. Which contains the creation operators. So it's somewhat confusing that the plus sign doesn't have the dagger, but and it has a minus sign here, but it's just, I guess the historical naming convention is we name this phi plus after the fact that these are contain the positive frequency modes. So, but the minus contains the plus sign and the dagger. Okay, so let's just look at the simplest example to see how we can relate a time-ordered product to a normal ordered product. So the simplest time-ordered product is the time-ordered product of two fields. And for x naught greater than y naught, fields are already normal ordered, or time ordered. And so let's see how we can relate this product of fields to a normal ordered product of fields. So to do that, we can expand phi in terms of its positive and negative frequency parts. And so there are four terms here. Three of them are already normal ordered. So phi plus is already normal ordered. It only contains annihilation operators. As is phi minus only contains creation operators, so that's already normal ordered. So the only two we have to worry about is ones that contain both creation and annihilation operators. And so phi minus contains a creation operator, so we want that to be the left. So this term is also normal ordered, phi minus of x, phi plus of y. And the last term is not normal ordered, but we can make it normal ordered by using the commutation relations. So we can write this as phi minus of y, phi plus of x plus the commutator. Phi plus of x, phi minus of y. Okay. And so that's what we get if x naught is greater than y naught. In the other case, y naught greater than x naught, it would be the same result, except the commutator would be different. Would be phi plus of y, phi minus of x. And so it's useful to define shorthand notation for the extra terms we get. And so we define the contraction of two fields, phi of x, phi of y. So contraction is just defined by drawing a line between them. It doesn't matter if the line is above or below. And this is just defined to be the extra terms we get. The difference between the time order, the commutators, the difference between the time order and normal order product. So that's just Heaviside function x naught minus y naught times phi plus of x, phi minus y plus the opposite if time ordering is reversed. And
What are those symbols again?
which symbols?
Like that lines, or you just
This line?
Yeah.
So this is what's called the contraction of these two fields.
Just I mean just lines.
It's just I draw a line between the two fields, and this is a definition of this expression,
Oh, all right.
and it means this. This is the definition.
Did you say that was the difference in the two? Or is it?
So time ordered product is equal to the normal ordered product plus this commutator, and which commutator depends on the sign.
Okay.
So the commutator, the time ordered product is equal to the normal ordered product plus the contraction. And this is the simplest example of Wick's theorem. Okay. And this expression in the top line should look familiar from a few lectures ago. We've introduced a new notation, this phi plus phi minus, but this is essentially just the same quantity we computed when we computed the Feynman propagator. So this contraction of two fields is this is the same expression we computed a few lectures ago. This is just the Feynman propagator from x to y. Remember, so a few lectures ago we computed the expectation value, but remember that the commutator of free fields is just a number. So the operator, the operator phi x, the commutator phi x and phi y is equal to its expectation value. So those are the same things.
How come? Again, I mean, there was a question. How can we understand that mathematically? Like we are multiplying operators, then we just get a number.
It's certainly a special case, but there's no reason why we couldn't. I mean,
Like I don't know. I just imagine. Okay, so if I have two matrices, then
well,
it's not the
I just
same.
say a complex number times the identity operator, if you like to think about it that way.
oh, okay. Oh,
That's probably a slightly more careful way to state it. But
Okay.
that's what I meant. Okay. So this is the simplest example of Wick's theorem. And Wick's theorem is just the generalization of this statement to any number of fields. So Wick's theorem says that the time-ordered product of n fields is the normal ordered product plus the normal ordered product of all possible contractions, including partial contractions. And here I'm reintroducing the notation from yesterday that phi1 is equal to phi of x1. Phi I is equal to phi of xi. And so what does this mean? All possible contractions. So for example, we have 3 fields. Wick's theorem would say that the time-ordered product is the normal ordered product plus all possible contractions, and there are 3 of them. Contract phi1 with phi2, phi1 with phi3, or phi2 with phi3. And in all 3 of these extra terms, there's one uncontracted field. That's fine. So why is Wick's theorem true? So we already showed it for 2 fields, and the simplest way to demonstrate it is using induction. And so let's assume it's true for some number of fields and show that then it works for one more field. And it's m minus 1. And we'll show it works for m. And also assume that x1 naught is greater than x2 naught, etc. is greater than xm naught. Otherwise, we could relabel. So this would just simplify the time ordering. And so if we apply Wick's theorem to all m fields, we get same thing as if, well, we can write this as phi1 times t, the time ordering products, phi2 up through phi m. Then we can apply Wick's theorem to time ordered product of phi2 through phi m. Gives us phi1 times the normal ordering of phi2, phi m, plus the normal ordering of all contractions that don't involve phi1. And we can write phi1 as phi1 plus phi1 minus. So all that's left to do is bring phi1 plus, phi1 minus inside the normal ordering. That's easy to do for phi1 minus because phi1 minus only contains creation operators. So we can bring this in. that just leaves phi1 minus. And let's look at the first term. Sorry, phi1 plus. Phi1 plus times phi2 up through phi m is the normal order product of phi2 up through phi m phi 1 plus the commutator, phi 1 plus the normal order product, phi 2, phi m, which we can write as phi 2, phi m, phi 1 plus the normal ordered normal ordering of the commutator phi 1 plus, phi 2 minus. So to commute past everything, we just have to commute past each of them. And so on up to phi 2 to phi 1 plus phi m minus. But each of these terms are just what we would get from the contraction of phi 1 with each of phi 2 up through phi m. So this is just phi 1 plus phi 2 through phi m plus phi 1 contracted with phi 2 up to phi m plus phi 1 contracted with phi m, etc. And the other terms will work similarly. So we'll just get the completely normal ordered term. And we'll also get all possible contractions that do involve phi 1. So this this works. So it holds for m fields as well. So since we already showed it for two fields, it works in general. OK, so that's Wick's theorem. And now we have all of the tools we need in order to compute scattering amplitudes. So, one last comment about Wick's theorem is that because the normal order product, the expectation value of the normal order product of any number of fields vanishes, only completely contracted terms are interesting. Only completely contracted terms contribute to the time order product, which is what we're interested in computing.
Frank, may I ask what you mean by completely contracted terms?
Completely contracted means that every field is contracted with exactly one other field.
So for example, there are none of them.
For example, none of these terms are completely contracted. Therefore, the expectation value of that time order product field is 0.
And that's true for all time-ordered products of an odd number of fields.
That's right. Okay. And so now we have all of the ingredients we need in order to compute scattering amplitudes. So we can go from the scattering amplitude to a time-ordered product of interacting fields using the LSC reduction formula. We can then go from time-ordered product of interacting fields to the time-ordered product of free fields by going to the interaction picture. And then we can compute those time-ordered products of free fields using our result for the Feynman propagator and Wick's theorem. We have all the ingredients we need. It's a rather lengthy path, given what I've shown you so far. But in principle, we can do it. However, there's a more direct and somewhat more intuitive way to do it that's completely equivalent to what we've learned so far. And that's the method of Feynman diagrams. And so that's what we're going to talk about next week. And we'll both discuss how they work and how they're related to what we've done so far. So we'll see that each of the steps in our process for computing scattering amplitudes is related to some of the Feynman rules for associating numerical expressions with diagrams that describe what's going on in the scattering processes. So that's what we'll do on Monday.
So this approach is perturbative or not?
So the step where perturbation theory entered, so we derived, probably erased it already, but the expression that related the time-ordered product of interacting fields.
Yeah.
So we had an expression that involved the time-ordered product of the interaction picture fields and the exponential.
Yeah.
So divided by numerator. So this formula is exact. The right-hand side is difficult or impossible to evaluate exactly. So that's where perturbation theory enters when we expand the exponential up to some order. Are there any other questions?
So you define the contraction when the fields are adjacent, but like, how does it define when there's another field in the middle? Say, like,
So, okay, so if there's another field in the middle, so we could say that phi, say phi1, phi2, phi3, contracted like this, is the same as phi2, phi1, phi3, which is also the same as phi1, phi3, phi2. So all three of these expressions are the same, and that's because the contraction is, after we contract it, we just get the Feynman propagator, which we can think of as either proportional to the identity operator or just a number.
and it's fine even if the field though.
Okay, at least, yeah. So we're only going to run across expressions like this. So this is true. After we normal order. Yeah, we'll never run across any expressions that don't have the normal order in there. Any other questions? All right, so homework 1 has been posted. It's due a week from today.